So this is a quick review of Euler's method. We're going to have a first order differential equation. So we're going to have y prime is equal to some multivariate function g of x comma y. And I want to note that when you see y prime, you actually have dy over dx. So it's a function in terms of x. And we also have initial conditions that are going to be x naught comma y naught. And also here I would like to note that y naught is equal to the function that's the solution to the differential equation y at the point x naught. Alright, so the way this works for Euler's method is that we have an initial point. I'll put the point right here. This is my point x naught comma y naught. This is my x-axis and this is my y-axis. And we know what the slope is. The slope at that point is g of x naught comma y naught, because you see this is the slope. That's what the derivative tells you. Now the question is, what is the next point? So I want to move it over a little bit. So if I move x naught plus h and I call that point x1, the question is, what should y1 be? Well, we already have the slope and we have a point. So we're going to use point slope formula. So recall that point slope formula works like this. Y minus y naught is equal to the slope times x minus x naught. Okay, so now, just like in Calc 1, if you have a point and you have a slope, you can approximate what the next point should be on the curve. So we're going to approximate y of x naught plus h. So i.e. x1 is going to be x naught plus h, and our y1 minus y naught is equal to our slope, which is just g of x naught comma y naught, times x naught plus h minus x naught. And you see that the x naughts go away, and you have the difference y1 minus y naught is equal to g of x naught comma y naught times h. Now if we were to approximate y1, then we would get that y1 is going to be equal to y naught when I bring it to the other side, plus, and I'll put the h first in front of the function, times g of x naught comma y naught. And remember, this is to approximate what the function y of x naught plus h should be. Now, that's our first solution. The next solution is we just repeat everything. So the next one, you're going to get x sub 2. That's going to equal to x1 plus h. And our y sub 2 is just going to be equal to y1 plus h times g of x1 comma y1. That's our next solution. So in general, what you get is we get that x sub n plus 1 is the previous x plus h. And y sub n plus 1 is equal to our previous y plus h times g of xn comma yn. And this is our general formula for Euler's method. Okay, so the next thing we want to do is now improve Euler's method. You remember that after the first step, this is the approximation of x naught plus h. That's the first approximation. So I'm going to write that in red. Y naught, I'm reading this from this line here, y naught plus h times g of x naught comma y naught was because we already have an approximation for that value. If you remember, Euler's method actually gives us an approximation. So we're actually using Euler's method and then using a trapezoid method on top. Back at it, it's going to be approximation of y naught plus h times g of x naught y naught. All right, so now we have the improved Euler's method, or IED. And the way that works is you have the initial setup just like you have for Euler's method. So you're going to have y prime is equal to a multivariate function g in terms of x and y, with the conditions x naught comma y naught. Don't forget that note, just like before, y naught is equal to the solution to the ODE, y, evaluated at x naught. It's the initial point. So we have the exact same setup that we have before. All right, we have our point somewhere, x naught comma y naught. And just like before, we're going to start at x naught, and we're going to move over to x1, which is really just equal to x naught plus h. And that's our distance h from those two. Now what I'm going to do is I'm going to take the original differential equation, dy over dx is equal to g of x comma y, with the initial conditions that you have x naught and y naught. And then this is the whole trick to the improved Euler's method. I'm going to integrate both sides with respect to h, and I'm going to integrate from x naught, over here, x naught, to x naught plus h. And what that final form is going to look like is y of x naught plus h is going to equal to y naught, because that's the initial condition, plus the integral from x naught to x naught plus h of this function, g of x comma y of x dx. Now a couple things to note is that, just to make sure this works, if you set h equal to 0, then this integral, this whole integral, will be y naught. And if h is equal to 0, then you get y of x naught is equal to y naught, which is exactly the same thing that we had with our initial conditions. All right. So, the thing that we need to do now is we need to come up with a better approximation for this. And just like before, there's many different ways to integrate. Now, for the improved Euler's method, what we're going to do is we're going to use the trapezoid, or the trapezoidal method. Just like what you did before, when we approximated areas under the curve. Now to better see this, I'm going to go ahead and draw a picture so we can see this approximation really well. Okay, now remember, we want to approximate this integral. Now this is different than the other curve that we have up here, so I'm going to use different colors for that so that we can see it better. So here, this is my x, and this is going to be my y. And don't forget that I'm trying to compute the area of this trapezoid, which is actually coming from this integral here, okay? And I'm using this g function that I'm integrating over. So this first point is going to be x naught, comma, g of x naught, comma, y naught. So that's the first point. The second point is going to be x naught plus h, right? And the second point is going to be comma g of x naught plus h, comma y of x naught plus h. Now, one more little parenthesis there. Need another one. And what we're going to do is we're going to approximate the area with a trapezoid. And remember what a trapezoid looks like. It's coming down here. Now this part here is going to be x naught, and this is going to be x naught plus h. Okay? And here is the area that we're approximating it with. Now the question you may say is, wait a minute, what is this? Right, that term right there. We don't know what y is. If we knew what y was, we would already be done with the problem. We'd already solved it. So we need to approximate that value there. All right. Now the good news is, and this is why I showed you this at the beginning. So for this, I'm going to say, recall from Euler's method, that y of x naught plus h can be approximated. So that's going to be y naught plus h times g of x naught comma y naught. All right. Now, let me make a little bit of room here so I can have something to work with. So the first thing we do is figure out what the next values are going to be. So I have x1 is just going to be x naught plus h, and y sub 1 is going to be equal to, don't forget this y naught right here, this y naught goes right here. So I'm going to put this y naught first, plus, and I'm going to approximate this value here using the trapezoid method. So if I do that, I'm going to have 1/2 times the height of this value, which is just g of x naught y naught, plus the height of this value divided by 2 for the average for that, times the width, which is just h. So let me write that out. Now, instead of writing all these things together, because I'm going to put this together with this big mamma jamma, so I'm going to make the notation a little bit easier for you guys. I'm going to write this as, just call this one M1 plus K1. I just came up with two names to name them. So M1 is going to equal to this height, which is just g of x naught y naught. So that's just going to be g of x naught comma y naught. And then K1 is going to be equal to g of x naught plus h comma. Now don't forget, I'm going to use Euler's method on the inside to figure this out. So that's going to be x naught comma, or x naught plus h comma y naught plus h times g of x naught comma y naught. You see, so I made it a little bit easier because this is the height of the left-hand side and this is the height of the right-hand side where I used Euler's method to approximate. So again, that's Euler's method right there. Now that you have that, just move this over here, you can repeat. Just like you did for Euler's method. So I'm going to say x of n plus 1 is going to be equal to the previous x plus h. And my y sub n plus 1 is going to be equal to, and that's going to equal to y sub n plus the trapezoid, which is 1/2 the average of the two heights. So I have m n plus 1 plus k sub n plus 1 times the height, where you're going to have m sub n plus 1 is going to equal to just g of xn comma yn, the previous value, and my k sub n plus 1 is equal to, this is going to be g of x sub n plus h, which is really, we've already actually done that calculation, that's actually right here, so you can actually use that value when you program it, comma, y sub n plus h times g of x sub n comma y sub n. Now this is called a predictor-corrector model because what you've done is you've actually computed Euler's method in the process. So this is sort of like a prediction. But then you put it back into the g function in this form to make a correction. So you actually predict Euler's method and then you correct it. So that's why it's called a predictor-corrector model. So this is actually what I want you to know, which is the improved Euler's method. So that's the improved Euler's method. And that is the part I want you to know and how to program. Lastly, before I move on, I want to say that all the other methods for the improved Euler's method, and eventually we'll get to the Runge-Kutta method of order 4, but all of those methods are basically using approximations for this integral. So if you can approximate this better, the better the numerical solution is for the ODE. Now, there was no reason why we just used 2 points. In fact, the Runge-Kutta method of order 4 and the Runge-Kutta method of order 2, or 4, 8, whatever they have, all these variations, is basically just different approximations for this integral. So if you approximate this integral in any different way, you have just now created a brand new numerical method. So since this is the basic idea, this is pretty much as detailed as I'm going to get, because we start doing the Runge-Kutta method of order 4, I'll say, or order 2 or some other variation, I may say, well, just approximate the integral with Simpson's rule, and you get a better approximation. Or approximate it with maybe a higher order polynomial. Then you get, again, a better approximation and higher orders. All right, that's it, except I feel like I'm forgetting something. Oh, yes. Don't forget to hit like and subscribe and all that other good fancy stuff. And here's a meme. Please don't post it on Reddit because it was made by Meme Generator. And I'll see you guys in class.